I think we're in trouble, Charlie. Even when we capture these things, they're damaging the ship with their energy.
I know, Ed. Each one is a different size. But on the graph, they all go through one point, making the energy too concentrated there.
To this point, we have found a general equation for sine waves. Y equals A sine kx. We found that by changing factor A, we could vary the amplitude. And factor K controls the period. Amplitude is fairly straightforward. For the curve y equals 3 sine 2x, the amplitude is 3. The period is more interesting. The standard y equals sine x curve has a period of 2 pi. We've also seen that the period of y equals sine 2x is pi. So if we divide 2 pi by this factor 2, we get the period, pi. In the general equation, this factor is k, so the period of y equals sine kx is 2 pi over k. Let's try y equals 5 sine 2/3 x. The amplitude is 5, so the curve meanders between these lines. K is 2/3, so the period is 2 pi over 2/3, or 3 pi. And the curve looks like this. Now we'll look at the cosine function, which has its roots in the unit circle. The cosine ratio is adjacent divided by hypotenuse. In a unit circle, the hypotenuse is always 1, so the cosine ratio is just equal to the length of the adjacent side. Let's see what happens to the cosine ratio as the angle goes from 0 to pi over 2. The cosine starts at 1, but gets smaller as the adjacent side becomes shorter, and at pi over 2, it's 0. Setting up a table. When x equals pi, the cosine is minus 1. Cosine of 3 pi over 2 is 0, and cos 2 pi is 1. When we plot y equals cos x, it seems to resemble the sine curve. In fact, as we see more of the cosine curve, we find it's exactly the same as the sine curve, except that it's shifted on the x-axis. Any shift on the x-axis is known as a phase shift. If two waves don't line up exactly, then they are out of phase. In this case, the curves are out of phase by pi over 2 radians. We can measure phase shift by starting with a wave in standard position. Then, shifting it to a new position, we can measure the angular difference on the x-axis. The graph of y equals sine x has undergone a phase shift of this distance, minus pi over 4 radians. Minus because the shift is to the left of standard position. However, the equation for the new curve is y equals the sine of x plus pi over 4. In general, a phase shift of minus d results in a curve described by y equals the sine of x plus d. And a phase shift of plus d to the right results in a curve described by y equals the sine of x minus d. Let's look at the graph of y equals the sine of x plus pi over 4. First, we graph y equals sine x. The angle in the equation is x plus pi over 4, so the phase shift is minus pi over 4. This means that every point on the curve is shifted to the left by pi over 4. We can also graph by means of a table. For y equals the sine of x plus pi over 4, let's choose some standard angles. Now, add pi over 4 to each angle. A calculator gives the sine values. On the plane, the points look like this, but it's not obvious how to connect them to form a sine curve. We need something else. We know that the equation y equals the sine of x plus pi over 4 has a phase shift of minus pi over 4. So the curve must start here. We know it's a sine curve, so it should look like this. With no factor here, the amplitude must be 1. Let's check x equals pi over 4, which is halfway between these 2 points. Adding pi over 4 gives pi over 2, and the sine value is indeed 1. If it crosses the x-axis at 3 pi over 4, we should get 0. And we do. And we can safely complete the curve. Now let's have a look at the tangent function. If we go back to the unit circle, we find that at 0, the tan ratio is 0. As the angle increases, the opposite side grows larger and the adjacent shorter. At pi over 4, the sides are equal and the tangent is 1. At pi over 2, the opposite side has lengthened to 1, but the adjacent side is now 0. This means that the tangent ratio is undefined. Let's plot the tangent values of several angles. The graph is periodic, repeating itself at intervals of distance pi. But as the graph approaches these points, the amplitude gets out of control and the curve is full of gaps. The tan ratio is undefined at these pi points because the adjacent side is 0, and therefore we're dividing by 0. These straight lines are called asymptotes, and while the curves get closer and closer, they never touch.
Okay, Ed, let's apply a phase shift to some of these sine waves to relieve the pressure at that one point. No, Ed, not the tangent button. Ah!